Okay, so I'm going to take a look at some examples of how can we create certain types of functions that either are injective, are surjective, are bijective, or aren't any of those. Okay, now we've obviously looked at a lot of good examples where you create sets and you just find different elements and then you can map those elements back and forth. That's a great way to come up with a lot of counter examples. But if I force you to now say, what if we create infinite sets? So instead of just having just sets that contain 1, 2, 3, 4, 5 different elements, what happens if there's an infinite number of them? Now, this doesn't allow us to easily draw some type of mapping between those. We need to be able to create some type of clear-cut rule that defines where every element in the domain is going to in our codomain. So in this case, we're going to take a look at an example of a function f that maps the natural numbers to the natural numbers. So here we're talking about the integers. Those are just greater than 0. So we're not assuming zeros in the natural numbers here. We're just going to assume that's 1, 2, 3, 4, 5, and so on and so forth. So we want to look at a few examples. So surjective but not injective, injective but not surjective, bijective, neither injective nor surjective. So what I want you to do, if you're able to, is try this. So try this on your own first. If you want to pause the video and try it, great. I'll give you a hint after you pause the video, then you can try to repause it again after the hint if you would like the hint. So the hint that I'll give you is try thinking about piecewise functions. Piecewise functions is one of the easiest ways that we have to define certain features that follow rules based off of maybe not just a general rule that will always work. So if you got stuck trying them, try it again now. Feel free to pause the video knowing that a good hint is to try piecewise functions. Okay, so now if you've tried that and you still are stuck or you just want to see some other examples, I'll run through some ways that we could define this. Okay, so this idea of surjective but not injective. Okay, so if I have this piecewise function, I'm trying to figure out how is this going to be surjective, but it is not injective. Okay, so remember, surjective, every element in the codomain, so every natural number here has to have something that gets mapped to it. However, we're not saying that, so we're not allowing this to be injective. So we are going to have to force two elements to get mapped to the same thing. So I will say the smallest one I need is 1, right? And I'm going to say this is going to be if x is equal to 1. Okay, so I'm going to start just defining 1 gets mapped to 1. Now for the not injective to be true, I'm going to move on to the next natural number. So to have this fail with injectivity, I'm going to have both 1 and 2 are going to get mapped to 1, not injective. Now to show that it is surjective, I have to figure out how can I get all of the rest of these numbers. Well, I'm going to define a rule that if x is larger than 2, well, I'm missing 2, 3, 4, 5, and 6, right? But I'm starting with the next one, which is 3. So I'm just going to simply define this as x minus 1. So this element, or so all of these numbers, so this would really be saying x is greater than or equal to 3, right? So if I plug in 3, I get 2 as my output. Plug in 4, I get 3. Plug in 5, I get 4, and so on and so forth. So every element in the codomain is going to be mapped to, but it is not injective because of this rule. So down here, injective but not surjective, again, I'll create a piecewise function. Now I need to figure out how do I skip something in my codomain. So how do we skip something? Well, I could simply start by saying f of x, I will say if x is equal to 1, I'm going to define this as 2, right? So if I just skip 1, I just have this. I could then move on and say, well, then if it's larger than all of these, then if x is larger than or equal to 2, I will do x plus 1. Now, this one, as we notice here, again, thinking piecewise function is a good way to start, but we don't even need a piecewise function in this case. We could have simply said f of x is equal to x plus 1. Every element gets mapped to the next largest element in the codomain, so we're going to skip the number 1. 1 is in the codomain, but it will not get mapped to anything because 0 is not in my domain. Now, bijective, there's a very easy function that's always going to be bijective, and that is just simply f of x equals x, right? But that's a very boring example. On exams or quizzes, I might specify, do not give me f of x equals x. Come up with a different function that also is going to be bijective. So you can think about this if you want, but now we need to make sure that everything in the codomain gets mapped to, and every different pair of elements here get mapped to something different in my codomain. So I could create a piecewise function where I'm going to map, if x is equal to 1, I'm going to map this to 2. And then if x is equal to 2, I'm going to map this to 1, and then I'll be x if x is larger than or equal to 3. So this is a great piecewise function. It's not the identity function. It's not just f of x equals x everywhere. I just do a slight switcheroo of 2 of the elements. That 1 gets mapped to 2, 2 gets mapped to 1, and then everything else just gets mapped to the same thing. So there's lots of other creative examples you can do for bijective. There's a whole lot of those. Obviously, there's an infinite number of all of these, but indeed, that one's maybe the easiest. Now, neither injective nor surjective. So we can try to combine some of our strategies taking place here. So we could, again, do something with a piecewise function if we want. We want to skip something. So I'm going to start with 2, and I'll say it's 2 if x is equal to 1. Okay, so I skip the number 1, make sure I don't ever go back to 1, and then I'll say it's 2 if x is equal to 2, and then I will say that it is x if x is greater than or equal to 3. So this is one where it is not surjective because 1 is in the codomain, but nothing gets mapped to it. It is not injective because both 1 and 2 get mapped to 2, but 1 does not equal 2. So I have the same output, but I have different inputs. So these would be some good examples to store in the back of your mind of coming up with ones for infinite sets.